Today, what I want to do is to show you how we take a data set from the bending beam rheometer and merge it with the data from a dynamic shear rheometer. This is something we do routinely to accurately get good information on the high stiffness part of the master curve. So I'm going to show you a couple of ways of doing this. And in doing this, I'm going to explain the files and how we process those files. So what I have here on my screen are basically 4 bending beam rheometer files. These have been captured from the Canon bending beam rheometer, and they are in the format .bbr as the extension. I have from these printed out the normal result sheets, and these result sheets are in PDF format and take the format of looking like this, where you can see the result in terms of time in seconds and the measured stiffness and the estimated stiffness from the results. You'll see that there's a % difference here. So as part of the normal process of running a BBR test and reporting the results, you look at these values in terms of the % difference, the M value, the load, check that they're all conforming to the ASTM specification requirements. Well, the bending beam rheometer data set contains more data than these 6 results. And the normal way we construct master curves is to try to get a minimum of 5 data points to represent a decade of frequency. In terms of these data sets, we have about 3 data points per decade of frequency. So we have 2 ways of trying to approach this. We can either take the full data set from the Canon or the ATS rheometer. So basically the software will work with any raw data format, or we can work with just this minimal data set. So let me first of all show you how we will work with a minimal data set. What we do is we set up a spreadsheet that looks like this. Now in my data set here, I've got 4 Canon results, and 2 at minus 30 degrees and 2 at minus 24 degrees. And I put into different columns here the stiffnesses that represent the results from the replicate at minus 30. So I have 2 replicates here. I'm calling these replicate A and replicate C. And then the 2 replicates from the minus 24 degrees. Now, what I typically do is to put in the measured values rather than the estimated values. These estimated values have the curve fit that's used in the analysis procedure in ASTM. But since we're putting this into software that also does curve fitting, I let the software do its own curve fitting. So I actually put in the measured values. So this is the data coming from the printout of the results that typically you get from a bending beam rheometer. I've then put this into the RHEA format. The RHEA format consists of a title line, and then it has this control line, and then it has the blocks of data representing the isotherm. So what I've done here is I've got minus 30 to represent the temperature. 6 is the number of data points here. And this final 1 just says it's including it in the analysis. So I have 2 sets of data. This number here is basically the average of the 2 stiffness values. So that's how the data is represented. 2 isotherms. And the isotherms of stiffness always go in the rear format from the coldest isotherm to the warmest isotherm. So we start at -30 here, we go to -24. And what I need to do is to take this piece of data here and to save this now as a TTD file. So to do that, I'll just start a text editor. I quite like this TextPad software. If I take this data set here, I'll just copy that here and paste that in to the software here for the TextPad editor. And I'm going to use this as the file name. So I'm going to call it U, which is the binder name. PAV is the aging condition, and it's a bending beam rheometer because it's a bending beam rheometer test. And I've added the number 6 here in brackets, so I know it's the 6-degree data set. So then I basically will save that, and I'm going to save that to my desktop and locate that in basically here. And when I do that, I just have to watch the file name that I'm going to save it to. I'm going to save it to U. This is a PAV aged material, BBR, and 6 data points, and it's a TTD file. We use a TTD file to represent time, temperature, domain analysis, and I'm going to hit save, and that will generate a file on my desktop. And the file that we have is this file sitting here, so UPAV BBR 6. And if I open that file up in text editor again, now you'll see it's very simply just that file in text. So this is the first option for generating a file format in a time temperature domain that Rheo will analyze. I'm going to save this Excel spreadsheet, and if anybody wants this, just shoot me an email, and I'll make this available to anybody watching this video. I'm going to save that Excel example just to my desktop again, and I'm going to call this the same thing, UBBR. Rather, I'm going to put the aging condition first, then BBR 6, and it'll save it as a XLS file in the desktop. So that's basically then available. If anybody wants that as an example, I can send that on. So that's the first way we can do the analysis, where we take the BBR and we put it into the format that Rheo is going to use. The next way we can do this is to use the Canon software. Canon software is basically available to download. This is a version I downloaded a few years back, but it enables me to open up these data files. Now the nice thing is, if you open up one of those files in here, so if I go like this, I find a file, look at the graph of the data, and you'll see that, you know, to generate this curve, there actually has to be a lot more data existing in that file. So if we think back to the ASTM standard says you have to collect data at every half second and record that. And essentially that's what we have in this data file. We have a lot of data recorded at every half second. So what we can do with this data set, I can take the data from these 4 files and I can do a batch export. So I can do a batch export here, take these 4 data sets in this location and do an export. And when I hit that export button on my screen here, you'll see another bunch of files appear. So if I hit the export there, and here they come, you can see these files are appearing down here. And these files now will basically contain the data in a half-second interval. So when you open up this data file, this is what we see in the data file. And you have columns of data that represent the force, the time, the deflection, and the temperature. And you'll see that these are in half-second intervals, and they go right throughout the test. If you make some very simple graphs, here we can go down to the bottom of this data set. So we're looking at 240 seconds as the normal test time, and then it has this recovery data at the end where the load is taken off. And what we see, just making a simple plot here, you have load going on and then the load coming off. Now, one of the things you'll notice is that this load doesn't come off completely. It still keeps that contact load on there. So because this contact load is sitting on there, we don't use any data associated with recovery. The other thing that we know is that we cannot use this startup data. If you look at the 0 time and you look at the 950, you'll see the 0 is 43, half a second is now 950. So it hasn't reached that full load in the half second. It's reached the full load round about, you know, this 1 to 2 second part. Dave Anderson and others have done analysis on this, and the conclusion is that the first 8 seconds of data, or any data before 8 seconds, really should be excluded from the analysis because of this load startup is not instantaneous, and also you can get something called a creep ringing effect that can affect the startup. So what we do is in our analysis in RHEA, if I look at the deflection, what we're trying to do is to take the data at 8 seconds and then get additional points representing the time to 240 seconds on a log basis within RHEA. And I'll show you how you do that at the moment. I'm not going to save this. I'm going to basically, this is in a CSV format. So when I close this file, it's going to lose that information, but then I'm going to read it into RHEA and show you how the analysis is done. So just close that file down and I'm not going to save that, but that's basically one of these 4 files that we have now made from the BBR data. The other data file that I have here is this file which we collected using dynamic shear rheometry. And this data file is already in the RHEA format. And if you want to know how to do that, I suggest you look at the manual or look at other tutorials about how to do that. What we have here is blocks of data that represent the results in dynamic shear rheometer PAV aged condition, and this is 5 degrees C data, and this is 15 degrees C data, and so on. I'll open this up in a little while and show you what this is, but the first thing we're going to do is go into RHEA and to start making the files for doing the analysis. So the critical files that I now have made is I have this DSR PAV here. I have a manual file I've made for 6 data points within RHEA. And now what I want to do is go and make another file that's a little bit like this PAV BBR file, but I want to make it using the data I've exported directly from the Canon software. So to do that, I'm going to start the RHEA software. I'm going to put this on a part of the screen, so I've got my files sitting here as well at the same time. So I'm going to move these files across. We're going to have that sitting here, and then we can see how that's looking. Okay, so what I'm going to do now, in RHEA, I go into the file preparation. I'm able to hit this raw button here, and what I need to do is find files that represent the bending beam rheometer dataset. Now, I have to go to this part here and change this to Canon BBR CSV. Even though those files showed up there straight away as possible files, I would get an error if I didn't correct this to the Canon format here. And you can see on the list there's an ATS format as well as the Canon format. So now I can go and select those 4 data sets and open those up in RHEA. Now, you'll see these are the isotherms of stiffness, whereas normally we would have isotherms of stiffness that are 8 seconds and then 15 seconds, 30, and so on, 60 seconds. What we've got here is it's added an additional data point in between. So it's added this one at 11 seconds, which is logarithmically halfway between 8 and 15, or as close as we can get. So we've added in these additional data sets, and these data sets now mean I am conforming with a rule which is to preferably have greater than five data points per decade of time or frequency. So you can see in this decade here, I've got 1, 2, 3, 4, 5, 6, 7 data points to represent the information. The results are reasonably close. You can see that there's 2 replicates here and 2 replicates here. So now I have a choice of how I want to save these data. I can put in a title here. So it's got the information from the files that they came from. It automatically puts that information here. But what I want to do is I'm going to call this, the material is called U. It's PAV aged. It's bending beam rheometer. And there's 11 points per set. So just to differentiate it between that other data set where I had 6 data points, I now have 11 data points here. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's put those data points in between the data points that we had earlier. So that's the isotherms of stiffness here. I can look at what temperature I want for the reference temperature. These are the other controls within RHEA. I'm going to set this at megapascals. And now I want to save this file, so I'm going to save it as a TTD file. And I'm going to save it basically as the same as I used earlier for this, but instead of 6, I'm going to change that to 11. So I'm going to put 11 in here, and we'll save that file. It saved another file with statistical information. That statistical information file basically just tells us where the data came from and contains the statistical information for that fit. So now I have these data sets. So I have basically created this data set here with 11, and let me delete that one. I don't need that one there. I have the UPAV BBR with 6, and I have this is the statistical information file, which I'm going to put over here for the time being. But I have this PAV6 and I have the PAV11. So the next thing is to convert these to time temperature domain analysis files that I can merge. When I look at the master curves with bending beam rheometer, I can't look at this. This is just a file preparation. So I have to open the bending beam rheometer files that I made, the time temperature domain format. So this is the 6 data set. I can look at the master curve. This is a creep compliance master curve. I can look at model fits like, say, the Christensen-Anderson, or we can look at in D of T as a reciprocal of that. So there's different models that we can look at. If I want to go and get delta TC, I can hit this button here, and I've got the delta TC sitting over here. So this is just coming directly from that analysis. And I can do a similar thing with the 11. Now, this one here was with the 6 data points per isotherm. And if you look here, we have this convert to dynamic data. So if I hit the convert item here, and that will now generate 2 more files. And you can see these files here have appeared over here. So let's get rid of that. And what it's done is it's got 2 files. I'm going to move those over here for the time being. And one of those files has got a E at the end of it, and one's got a G at the end of it. So it's done a conversion to the results in extensional format, and it's also done a conversional in the shear format. So this is converting the data to dynamic data, where I've now got a column representing G prime and another column representing G double prime. I can go and read that file in. So if I look at the this converted file, I'm looking for the G one because I'm going to merge this with a shear file. So I really want to see the G. So this is the G one here. And you can see now instead of an S of T, I've got G prime and G double prime. So the G prime and G double prime basically enable me to look at the data set in dynamic terms. And I can even go and get a little master curve. You can see this is a little master curve where I've got the data set in terms of G prime and G double prime, but expressed as a master curve. What I now want to do is go and merge this data with the dynamic shear rheometer data. So let me just open up that dynamic shear rheometer data and show you what that looks like. So the dynamic shear rheometer data for you was basically this data set here. I've already trimmed out a little bit of that data here, which I considered to be unreliable. This is at the 5 degrees and 15 degrees C part of the data set. If I look at the master curve that I have for that, this is G prime and G double prime. This is the black space. This is a modified binder, the SBS modified. You've got some behavior here that represents non-thermorheologically simple behavior. But what we want to now do is see where the BBR lines up over here. So I want to take this file and merge this file with the BBR, and I'm going to first of all merge it with the BBR6 data set, and then we're going to repeat the whole operation with the BBR with 11 data points. So let me go and do the merge. I go back into file preparation, and this time I'm going to take, rather than opening a raw data file, I'm going to merge 2 TTD files. But before I go and merge these files, I want to look and see how they compare in an overlap. So the overlap feature just enables me to open two dynamic shear data files and see how they compare. So I'm going to take, in this case, the DSR for the PAV and this result here, which is PAV BBR but in shear. So notice I'm picking the G format here. I can open up both of these files in this overlap feature, and they don't line up here because I've got different reference temperatures. The reference temperature for this data set is -24. The reference temperature for this data set is 25. I want to look at that in the black space. Make sure that this data set here is lining up reasonably well with this data set. If that's the case, then I can merge them. This is sort of going to 1e to the 9, which is where I'd expect to see it. And there's a little gap here, but this will merge reasonably well. So now I'm going to go back into my file preparation. I'm going to hit my TTD button. I'm going to take the file here, which is the G version, and then I'm going to take my DSR version here, open those up, and basically now create a merged file. So I'm going to go in here and just tidy up the title. So this is U, PAV. The next thing here is it's both DSR and BBR, and I'm going to put a 6 on the end here because it's the 6 data points from the BBR. And what else do I need to check here? What reference temperature I want for the combined data set. I'm going to use 25 for my reference temperature. I'm going to keep it in radians, and all of this other information I'm going to leave as it is. What I normally do is just copy that to the clipboard. So when I hit save here, I can just put that in there. And U, PAV, DSR, and BBR, and I've got 6 data points, and I'm going to hit that save there. Now I can open that up, and that file is this file here, and it now opens up in this space here, and I can now got a combined master curve. This is the bending beam rheometer part. This is my DSR part. If I want to make that look a little bit more fancy, I can display it by colors. I can then go into my other data sets and start to calculate all the other parameters that might be of interest. And, whether I'm after things like, the Pavel-Chris's phase angle or the Glover-Rowe parameters, or whether I want a viscosity curve, which I can get from this plot here. Now I have the data in a merged format, so that will cover a wider data set. And that's basically the process for doing the analysis, where we're merging two different data files. What I want to do now is take the 11 data point data set and merge that. So what I have to do first is to open that 11 point data set, which is this one here. It opens up here. Again, I could look at the data for this, the Christensen Anderson model fit or the delta TC if I want to, but simply I just need to convert this to those alternate files. So I hit my convert. So now I've got my 11 points in my data set. I've got an E and I've got a G. Just to see how those compare on an overlap, they'll be very similar. So I can go on here and there's my G, and then I can compare that with the DSR. Hit the open button there. It's doing that analysis. Again, these don't line up because of the differences in reference temperature, but if you look at a black space, which is independent of reference temperature, you see a very similar result to what we saw earlier. I can go back into my file preparation, hit the TTD, basically merge these two files, and I will change their file name to a similar one I used earlier. So this is going to be called UPAV. I'll make that a capital U. DSR and BBR, and I'm going to put an 11 behind that. Change my reference temperature to 25 again, and that's all I really need to have there. Copy that to the clipboard, so when I save it, I can just paste that file name in here and save that as my data set. So what that's done now is it's made this file, which has now got 11 data points, DSR and BBR. So my files that I'm interested in are these merged files. So this is the one with 6 points, and this is the one I have next to it is with 11 points. So those are the two data sets there. So let me open up that 11.1, and we can see, where's that gone? There's on top. So this is the data set that's now opened up. If I look at my master curve that I have here, this is the modulus and phase angle. This is the 11 data points representing each BBR isotherm. And, again, I can go and look at different data sets and different information regarding that. Now, one of the questions you might ask is, how close are these two data files to each other? So what we can do is we can basically open those up in the overlap feature, and we are now going to see how good a 11-point merged file is with a 6-point merged file. So I'm going to open those two up here. So I've got basically that's my 11-point, and this one here is my 6-point. And we're merging these two together, and we'll just see how the results compare. So those are the two data sets. You can see that the blue is the 11 and the red is the 6, and they sort of right on top of each other. If we look at the goodness of fit and the parameters that we see on the bottom here, this first parameter, discrete spectrum fit, tells us how good is it behaving in terms of a linear viscoelastic material. I've got slightly better fit with 11. A polyfit, that tells us how well the time temperature shifting has worked as a thermorheologically simple material. Again, slightly better with the 11 versus the 6 data points. And then we can start to look at some of these results. If you look at, say, some of these results like the Glover row number, you can see they're very similar. If we come along to, say, the work that Pavel Chris did, where we look at a phase angle at constant modulus, we've got 37.96 versus 37.94. They're virtually the same number, which is sort of what we expect. Let's come along the end here to where we have the R value 3.39 versus 3.38. That's using a 1e to the 5 limit. If I change that limit to, say, 1e to the 6, so we cut off all the lower part of the data, which is normally what I like to do. You can see we've got 3.4 versus 3.38. So these data sets are very similar. You get slightly better results if you export the data to 11 points versus keeping this data as 6 points, which you get in the automatic analysis. If anybody would like these data sets that I've used here, just send me an email. I can email you the data sets, and you can play around with this in your own version of RHEA. This data file is in the demo version in the original format, and that can be downloaded just by accessing a link. Any problems with that, again, just shoot me an email and I'll be happy to try to work with you and make sure that's available. But you know, I hope this is of use and of value, and this really explains how we do the merging. There's other techniques available in the literature. This is the method that we've implemented in RHEA. And thanks very much for joining us and listening. Take care. Bye-bye.